Good ozone? Bad ozone? What's the difference? And why is NASA interested in measuring ozone? Find out next on Real World. Have you ever lived in a city that posted an ozone alert on a really hot summer day? Just what does that alert mean and what causes the problem? It all goes back to basic chemistry. You see, the oxygen we breathe is actually a molecule made up of 2 oxygen atoms. So its molecular formula is O2. Ozone is an unstable and reactive form of oxygen that is made up of 3 oxygen atoms. So its molecular formula is O3. Now, that difference of 1 oxygen atom might seem insignificant, but it's actually a huge deal. Bad ozone, or ground-level ozone, is actually an air pollution problem that is created when pollutants like exhaust, paints, cleaning fluids, or other industrial emissions react with sunlight, creating more of the unstable ozone molecules. In the troposphere, which is the lowest level of Earth's atmosphere, and the one we're in right now, ozone's natural concentration is about 10 parts per billion, or about 100,000% of the atmosphere. That's really small. According to the Environmental Protection Agency, ozone levels greater than 80 parts per billion over a long period of time can cause throat and lung irritation or aggravation of asthma or emphysema. And that brings us back to those ozone alerts. When levels get high enough to cause problems, alerts are issued and people are asked to change their regular habits. Things like drive less, delay mowing, and stay inside if you have certain health conditions. Of course, not all ozone is bad. 90% of the ozone in our atmosphere sits in the stratosphere, the layer of our atmosphere between about 10 and 50 kilometers above Earth. Stratospheric ozone protects Earth's surface from excessive ultraviolet radiation. NASA astronauts on the International Space Station have an amazing view of our fragile atmosphere and the thin line that makes up the ozone layer. But why is NASA so interested in ozone? Well, let's hear from Dr. Joe Zawadny, a scientist at NASA's Langley Research Center.
In the mid-1980s, we discovered that there was an ozone hole in the Antarctic, and shortly thereafter we discovered that the global ozone layer was decreasing. We discovered the reason behind that was due to chlorine compounds released by humans. Chlorine was seen to peak and then started to decrease in the late 1990s. And we've seen global decrease in ozone flatten out. It now has a slight increasing trend.
In order to understand how ozone might be changing, it needs to be measured. The most common unit for measuring ozone is called the Dobson unit. 1 Dobson unit is the number of molecules of ozone that would be required to create a layer of pure ozone 0.01 millimeters thick. Of course, ozone isn't all packed into a single layer in the Earth's atmosphere. It's dispersed throughout it. Since NASA doesn't have a way to actually scoop up all the atmosphere and squeeze the ozone into layers, just how do we measure something that makes up less than 600,000% of our atmosphere? For over 30 years, NASA has used the Stratospheric Aerosol and Gas Experiment, or SAGE, family of instruments to increase our understanding of the atmosphere and our knowledge about ozone. And the latest generation, SAGE 3, is catching a ride on the International Space Station, bringing a whole new perspective to the problem.
So SAGE 3 measures ozone 3 different ways. We use a technique called solar occultation, where we look at the sun directly with the instrument and then look through the atmosphere as the sun sets or rises. We can also do the same thing using the moon. Moon's 1,000,000 times dimmer, so it's a little bit more difficult. And the third way is we can just look at scattered sunlight, look at the atmosphere and just look at the blue sky, if you will. And molecules like ozone have unique absorption features in them that are easily detectable. So when you see ozone vary, or if you're measuring surface temperature, if you want to know why you see the variability in the record that you do, you need to know what else is going on. So what the aerosols were doing, what some of the important chemical species that control ozone, what they were doing. And only by understanding that variability can you get at the underlying variability that you may not fully understand.
The measurements collected from SAGE 3 will provide valuable information to the global scientific community, helping us answer questions like, how is our global Earth system changing? How do human activities influence our climate? And what can we do to protect our atmosphere? And NASA scientists will search for those answers by using the data collected from SAGE 3 to tell the story. See you next time on Real World.